universal, what are called REST APIs, which is universal queries to all these databases, because there is a multiplication of databases, and it's probably very useful before it's too late to have just the common tools. And Jean-Marc is organizing a second workshop on this in June.
Thanks a lot, Nicola. And thanks also to the organizers for inviting me here. So it's really a pleasure to be here and to tell you a bit about the work that we've been doing on Materials Cloud. I'm going to briefly revisit some of the practical challenges that have driven the creation of Aida and Materials Cloud, and give a brief overview of the architecture of both tools. And then most of my time I'm going to spend on showing you some examples of what you can do with these tools today. So the first challenge has already been introduced by Geoffrey, thanks for that. It's a high throughput, so how do you organize large numbers of calculations in a consistent way? You all know this problem. The second problem is maybe what comes afterwards, right? So you have done your calculation, not necessarily a high throughput, but there's a lot of data sitting around. So that's like the story of the PhD student, Bob, who knows exactly how he did his calculations, where he put the data, but then he leaves the group, and the data is still sitting there, and the next PhD student, Alice, has to pick it up, and she gets lost in the data jungle. So how do we improve on that situation? Then there's the related open science problem. So say I've done my calculations, I've written the draft for my paper. How do I open access to all the data that I have in a meaningful way? And not many people do this nowadays because it is an enormous amount of work. And I think the key challenge here is how can we make this process easier? And finally, I've called this knowledge transfer, or we could call it dissemination. So what I'm thinking about is, say I'm collaborating with an experimental group. I've done some calculations for them, and now I would like to share this data set that I have with the group I would like to communicate this data set to them. And of course, they don't have the software I have to view the data, right? So I've often been in this situation, and I felt that making a few plots and putting it into a PDF was really not an optimal way of communicating to them what I wanted them to see. All right, this brings me to the second part. So this is the architecture diagram for Aida. Aida, in essence, is a collection of Python packages that you install on your local machine, so workstation or laptop, that allows you to set up, submit, and monitor material science calculations. Aida takes care of transferring the input files from your machine to the supercomputer, submitting the calculation at the supercomputer, monitoring the queue, and when the calculation is done, retrieving the results back to your local machine. And what sets Aida apart from other similar approaches is that you have a local database, and so this is a database sitting locally on the computer where you have installed Aida, and this is essentially a history of everything that happened. So Aida stores there for every calculation, let's say which inputs were used, where it was submitted, who submitted it, when it was submitted, which outputs were produced, etc. And this data is stored in a directed graph, and it is this graph that helps us with the open science and the data jungle problems. Aida is free and open source. It's developed in this GitHub repository. There's a number of plugins for different material science code available. And let me just say, so if you want to start developing an Aida plugin for your code, you just copy our plugin template that we provide and start from there. You can do that completely independently. It's a very modular setup. All we ask is that you please register your plugin on the Aida plugin registry. Just a little bit of information that is very helpful for you to reserve the name for the plugin, and it's also helpful for the Aida community to know that you're working on it. And who knows, I mean, somebody might come and help you. Now to the architecture of Materials Cloud. Materials Cloud, in essence, is a Angular JS web app that can communicate with an Aida database through a REST API. So this is what we call the explore section. So this is about exploring a database, an Aida graph, through the web browser. And there are 4 other sections. So there's discover, which is about providing user-defined entry points to an Aida database. There's work, which is about running and launching calculations in the browser. Learn, a number of, where you will find recordings of lectures and tutorials together with slides. And finally, there's the archive, which is a place where you can upload your research data, get a document object identifier for it, and then link to this data in your paper. But this is all very abstract, and so what I really would like to do is to show you a few examples of what this actually means. The first example is the SSSP that was already introduced by Nicola. So this is, again, is a collection of pseudopotential libraries, and for each element in the periodic table, it tells you which pseudopotential gets the job done with the lowest cutoff. So we go on Materials Cloud, beta.materialscloud.org, click on Discover, SSSP, and we are presented with a periodic table. Now the color indicates which pseudopotential library is suggested for this particular element. The number is the cutoff in Rydberg. And what I didn't say, there's 2 different versions of the SSSP, one intended for precise material modeling and one intended for high throughput screening. So now we're in the efficiency version, and it says for carbon, it suggests, in this case, a PAW pseudopotential from the PS library 1.0 with a cutoff of 45 Rydbergs. And that is all nice and fine, but how did it come to this conclusion, right? So I can click on the element, and well, I get an overview of different properties that were computed for the different pseudopotentials. I'm not going into that in detail. There's an equation of state versus an all-electron calculation, again, for the different pseudopotentials. And a few other plots like a cohesive energy as a function of wave function cutoff. And what I'm going to look at here is so the maximum phonon frequency is a particular Q point, again, for the different pseudopotentials. And this is all nice and fine. So this, if say if I'm mainly interested in converged phonon properties, this plot can help me decide which pseudopotential to use. But the problem with these user-defined interfaces is that no matter how many plots you make, you will never be able to expose all the data you have. This is where Aida now comes in. So in this plot, actually all of these data points link to an Aida node. And when you click on the data point, you get to the node in the database. In this case, this is some post-processed data from an Aida calculation. You can see who did it. In this case, it's Gianluca Prandini. And then here, using this provenance browser, you can go up the Aida graph and see where this data came from. So this is, if you jump over this Python function that did the post-processing, you eventually get to the node that represents the calculation for the phonons. So you can look at the input file that was used, or any of the outputs. For example, if you want to download the dynamical matrix. And here again in the provenance graph, you see all the different inputs and outputs that went into this calculation. And of course, one of the inputs is, for example, an SCF calculation that was done with the PW code. So you can go further up the provenance tree. By the way, note that this is not done by Gianluca Prandini. So somehow Nicola Monet was able to, Gianluca Prandini did the post-processing of the calculations that were done by Nicola. Right, so here we are now at the quantum espresso calculation. And well, one of the things that you can see here is now the structure. So the structure, for example, is something that you did not get from the plots. It's not included in our interface because we didn't think about including it. But you might want to know that the structure that was used to do these convergence calculations is actually graphite. Or what you might want to do is, say you have a new pseudopotential that is not in our list. You want to redo the convergence tests using exactly the same parameters as we did to make them comparable. So you download the input files and you redo the calculations. And then if you if you're not happy with downloading individual files, but you want to have everything, sorry, this is not what I wanted. You go to the archive section, you find the entry for the SSSP there. So there's a DOI that will be cited, I guess, in the archive paper. And you can download the whole Aida database. You can download an archive of all the plots. And basically import it into your Aida instance and start your calculations from there. For the second, so there's also an example of, there's also a section for the 2D materials work that Nicola showed earlier on. I don't have time to show all of that, but you're very welcome to have a look on materialscloud.org. So I will jump over that to the phone workflow, which is another example of what Nicola showed, but now we're going to look at this in a slightly different way. So this is part of the work section of Materials Cloud. So we go to Materials Cloud, go to work, and click on the Jupyter button. And what happens now is, at CSCS, there's a Docker instance started for me. And in this Docker instance, there's a Jupyter Notebook server. And what I see now is nothing but the Jupyter Notebook that is rendered as a web app. And down here, we have the phone on workflow that Nicola talked about. And while it is true that it is very easy to use, what Nicola didn't tell us is that, of course, you still have to set up the machine on which this workflow can run, right? And setting up this machine, you need to know a little bit about how to install Aida, how to install Jupyter, etc. And this is something that Materials Cloud takes away, right? So in Materials Cloud, you log into Materials Cloud, you go on your page, and you start the phone workflow. There's no setup. And this brings me to another key message that I would like to give. So the reason we use Jupyter Notebooks and Python here is not because they give you the most fancy user interface, they do not, but because they are, we believe firmly that this is the simplest way of writing these apps. And so what we're going to do now is we're going to edit this app live and add another example input structure here. So at the moment we have 4 input structures, so let's add silicon. So we click on edit app. All of this is now this is the source code of this app. Everything is editable, so also the text, which is simply marked down. And now we simply search in the quell code for the first occurrence of diamond, which was the first element in the list. So this is the list that generates the drop down. So this is essentially what I did when I modified the app, because I didn't write this app. It was Giovanni Pizzi and Nicola. And I thought, let's make an example of how to add a new structure. And one thing is the drop-down list. Another thing is you need to actually generate the crystal structure to give to Aida. This is just 4 lines here. And why is that? It's because it's using the crystal function from the atomistic simulation environment, which just needs the atomic, and just the element, the position in the unit cell, the space group, and the cell parameters. And of course, silicon has the same space group as diamond, so we essentially just need to change the lattice parameter and a few variable names, and that's it. So when we're done, we click on save, and we go back into app mode, and now we should have added silicon to the input structures, and we can submit we can submit the formal calculation with silicon. So this was not sped up, that is real time, and the message that I would like to give is if you know how to program Python, and if you know a little bit of Aida, then you can write such a workflow. I'll skip over the results because I want to show another example, which is from another group. This is from the Nanotech at Surfaces laboratory at EMPA in Switzerland. This laboratory is a mixed theoretical and experimental laboratory. And one of their main lines of research is the synthesis of atomically precise graphene nanoribbons. And so the experimentalists have every now and then they ask the theory guys, could you please investigate this structure because we might want to synthesize it. And what they did is they programmed both workflows inside Jupyter and interactive ways to browse the results that they obtained, the calculations done using Aida. So this is an example of browsing their Graphene nanoribbon database. So this is a very specific user interface for this use case, right? You see like the structure of the nanoribbon and a few properties. And now you can interactively explore some of the properties of these nanoribbons. For example, you can compare the band gap of these two nanoribbons. Click compare. It starts a small work function, a small, let's say, calculation that runs, I think, in this case, directly on the virtual machine, which simply plots the two end structures side by side together with the Fermi level. Another thing you can do is you can show the projected density of states. So this might be interesting if you're designing the edge of the nanoribbon, you will want to know which atoms are particularly important for density of states near the Fermi level. So by default, it shows the full density of states for both spin up and spin down. And then you can select one atom, and if you wait a little bit, it shows you the density of states predicted on this particular atom. Again, this is also something that experimentalists might want to do. And finally, you can have a look at the local density of states. So this is very important for this group because they do scanning probe microscopy, in particular scanning tunneling spectroscopy. And so you can select a particular band structure, and what it shows you here is now the local density of states on top of the ribbon at a particular height for this particular K point. So this is something that you would get if you do, for example, a constant height scanning tunneling spectroscopy scan over the ribbon. And this is something that experimentalists can directly compare to experiment. And below here you have the spin density, which is another thing that they are interested in. They can download the picture and put it into their presentation. So they were, in the beginning, the experimentalists were quite skeptical about about getting this work started. It sounded like a lot of work, and was not. They said, okay, maybe I'm not sure whether this is going to be useful, but they have since changed their mind. So this is from the head of the experimental laboratory, and he can use this interface for comparing band structures, for looking at the properties of these ribbons, and well, I would say they have been won over. Let me mention one last thing, and that is quantum mobile. So what is quantum mobile? Quantum mobile is simply a virtual machine image that you can load into the VirtualBox software that runs on any operating system, right? So Windows, Linux, Mac OS. And what this takes away from you is the necessity to set up Aida in Jupyter. So inside VirtualBox, you have Aida in Jupyter pre-installed. You have all of the max codes pre-installed, plus CP2K, as well as there are Aida plugins, so they are ready to be used through Aida. So if you have like a lecture where you would like to use Aida, this is something that you might want to use. And the last point I would like to emphasize is that this is by design, this is a very modular setup. So we don't just have the virtual machine image, but on GitHub we also have the scripts to set up the virtual machine. And if you need for your lecture some additional tools that are maybe not so easy to install, or you have some other modifications that you need, you simply go there, you clone the GitHub repository, you make a few adjustments, and you produce your own quantum mobile. So let me conclude. So Aida is our way of dealing with the high throughput problem, and in particular the Aida graph is our map to the data jungle. What I can promise you today is that if you do your calculations with Aida now, they are ready for open science. Materials Cloud is a younger project. It's now in a public beta. But the archive is now accepting submissions from our partners. So if you're affiliated with MAX, for example, and you're very welcome to check it out. And about the Jupyter part, so my main message is it is simple to write. Also there, the workflows are shared on GitHub. And yeah, run it wherever you like, right? Run it on your own machine, run it on Quantum Mobile, or run it in the Materials Cloud. I'll have to acknowledge the many people who are working tirelessly to make Materials Cloud and Aida better and better, both at EPFL and also elsewhere. And with this, I thank you for your attention.